Okay, in this lesson we look at the general sine function of the form y equals a sine of b brackets x take c plus d, where always we take b being a positive number, and a, b, c and d are parameters. An example of this would be this one here, where clearly a is 2, b is 3, c is pi and 4, and d equals 1. And what we're interested in is how we can transform a graph of y equals sine x, our basic sine graph, to form a graph of the one that we want. Let's first look at what we mean by transformations. Well, transformation in English just means to change, alter or modify. And in maths, it's the same. We transform or we change or alter a shape or a graph. So what are the types of transformation in maths? One is a translation. That just says to move an object from one position to another. Here's the object and it's been moved from here to here. Where it ends up, or the figure that we end up with, we call the image. Now this one has clearly been moved 3 units to the right and 1 down. So we say the translation is made up of a horizontal component of +3, 3 in the x direction, and a vertical component of -1, 1 down in the y direction. Or sometimes it's just summarized as a vector, t brackets 3, -1. So that's our first type of transformation in maths. A second type is a reflection, where we have an object or a graph, and we want to know what it would look like if we reflect it in an imaginary mirror line, in this case a vertical line. So clearly the reflection in that mirror line would be our image here. Third type of transformation is a dilation. Now there's two types of dilation. One where the object is enlarged, becomes bigger. Is it stretched? And in this one, you can see that every length here is about twice what it is here. So we say the scale factor is 2. Then we can also have where an object is made smaller. That we call a reduction or a compression. And in that case, the scale factor, in this case, every point or length in this image is about half what it is here. So we say the scale factor is a half. In general, if the scale factor is greater than 1, it's an enlargement. If the scale factor is 3, the figure is made 3 times as big, or it's stretched 3 times in a certain direction. If the scale factor is less than 1, it's a reduction. And there's a fourth type of transformation, a rotation. Here the object here is being rotated 90 degrees clockwise to produce this image. Now that one we don't have to worry about in this work. So we've already come across this in previous work, transformation of basic graphs, say transforming y equals x squared. If you wanted to get a graph of y equals x take 2 squared take 1, we know we do a horizontal translation of 2 and a vertical translation of -1. So y equals x squared, here it is. Every point on this graph has been moved 2 to the right and 1 down to form a graph of this one. If we wanted to get a graph of y equals -x squared from x squared, we know what we have to do is reflect in y equals 0, or in the x-axis, as the mirror line. So here's y equals x squared. To get y equals -x squared, we reflect in the mirror line y equals 0. Every point on y equals x squared becomes, the y value becomes the negative of that on y equals -x squared, of course. Dilations. Again, as we said, there's two types of dilation. One where the scale factor is 3, that's an enlargement, where if we wanted to produce a graph of 3x squared from x squared, we'd stretch vertically by a factor of 3. Here's y equals x squared. Every point or y value on that is multiplied by 3. So here's 1, 1. becomes 1, 3, and so on. If we wanted to get y equals 0.5x squared from x squared, here the scale factor is a half, so it's a reduction. Here's y equals x squared. Every y value on y equals 0.5x squared is a half its value on y equals x squared. So we've come across these before. Now we need to apply them to a function like this, a sine function. How can a graph of y equals sine x be transformed to form a graph of y equals 2 sine, etc., etc., etc.? Well, there's 4 steps. The first step, we think of sine x and sketch it, and then we'll sketch from that a graph of y equals 2 sine x. Now the 2 here indicates to me that we need to stretch it vertically by a factor of 2. In other words, vertically dilate with a factor of 2. The dashed line here is sine x. Every y number is doubled to form 2 sine x. First step done. Then we work with 2 sine x and we draw a graph or sketch a graph of 2 sine 3x. The number here tells me that this is a horizontal dilation of 1/3. We have to horizontally dilate y equals 2 sine x with a scale factor of 1/3. So we started with, the dashed line now is 2 sine x. If I horizontally dilate by a factor of 1/3, instead of one complete cycle being in 2 pi, now there'll be 3 complete cycles within 2 pi. 1 cycle, 2 cycles, 3 cycles. And we can see now the period has become not 2 pi, but it's become this distance here, which is 4 squares. And if you think about it, because I've done 1 square is pi on 6, 2 squares is pi on 3, 4 squares will be 2 pi on 3. So the period is now 2 pi on 3. 1 complete cycle in 2 pi on 3. So there's the second step. Now we have a graph of 2 sine 3x. We work with that and we look at the number here, pi on 4. That tells me to do a horizontal translation of pi on 4. So the dashed line now is 2 sine 3x. Now to translate pi on 4 to the right, every point has been moved 1.5 squares. How did I figure 1.5 squares? Well, if 1 square is pi on 6, 2 squares is pi on 3, pi on 4 is halfway between pi on 3 and pi on 6, isn't it? So pi on 4 must be 1.5 squares, 1.5 squares. So every point on 2 sine 3x is moved 1.5 squares to the right. And that's how we sketch 2 sine of 3 brackets x take pi on 4. Third step done. The last step is to do with the +1 here. Now that's very easy. It just means that we have to move everything up 1. In other words, translate vertically by 1. So we start with this graph, which is our solid line here, and move every point up 1. So the dashed line is this one. Every point you can see has been moved up by 1 to get our final graph that we want. In summary, here's the final graph that we got. Now, I've typed that in this graph into Desmos and plotted it, so you can see actually we do end up with the correct graph. If you can compare this one and this one very closely, you can see that other than my errors in plotting, it's pretty much identical. So let's look at this, focus on this one now, and do a bit of a summary. What can we determine from this? Well, we've learnt that there are certain features that we talk about. One is the principal axis. And you can see the principal axis is y equals 1. That is the line which the point, if you like here, oscillates about. It's the mean line or the average line. And we also learnt that you could calculate that by max plus min divided by 2. In other words, 3 plus -1, which is 2, divided by 2 is 1. The principal axis is y equals 1. Another feature is the amplitude. Now that's the distance from the principal axis, the maximum displacement from the principal axis. Well, from 1 to 3 is 2, and going downwards from 1 to -1 is 2 also, so the amplitude is 2. Or another way to work it out is max take min divided by 2. 3 take -1 is 4, divided by 2 is 2, gives us an amplitude of 2. And lastly, the period is 2 pi on 3, as we talked about earlier. It's 2 pi divided by this number here. Or there are 3 complete cycles over 2 pi. Here is 0 to 2 pi. And you can see there is 1 cycle, 2 cycles, and 3 cycles in that. So the period is 2 pi over 3. And just summarizing again the transformations that we had to do. We started with y equals sine x. We did a vertical dilation with a scale factor of 2. This is the number which tells us the vertical dilation that we need to do. One thing to look out for, or we'll talk about that in a minute, that if the scale factor, if the number here is negative, we also have to reflect. The horizontal dilation, a scale factor 1 on 3, which comes from here. And then a translation of pi on 4 right, number from here, and 1 up, the number from there. There we have it. So if we want to generalize for the general sine function, this number we said affects the amplitude. And if we're transforming the dilation, this number affects the period, and the period is 2 pi divided by b. This number affects the horizontal translation. This one affects the vertical translation, and there's also the equation of the principal axis, y equals d. And the amplitude, as we said, is the absolute value of A. Remember, the absolute value just means the magnitude of. So the absolute value of 2 is 2, the absolute value of -2 is 2. And the transformations, y equals sine x is dilated vertically with a scale factor of absolute value of A. If A is less than 0, you also need to reflect in the x-axis. Then once we have y equals A sine x, we've did the next step. That is dilated horizontally with a scale factor of 1 on B, and then we do our translations of C, D. C horizontally and D vertically. All right, so there's the summary. Now let's look at some examples. State the transformations that map y equals sine x onto y equals negative sine 2 brackets x plus 1 take 3. Now you might want to stop the video and try and answer that for yourself, and then restart to check your work. Okay, here's our thinking. Here's the solution. We can identify the general numbers. A is -1, B is 2, C is -1, because this is x take -1, and D is -3, that should be a mistake there. So there's no vertical dilation since the absolute value of A is 1. But the -1 means that we must reflect Y equals sine X in the X-axis first. B equals 2 means that we horizontally dilate by a factor of 1/2, or compress by a factor of 2. C equals -1 means we translate 1 unit left, and D equals -3 means we translate 3 units down. In red are what your answers should be, the transformations that map this into this. So there's that one done. Here's a couple of little questions. Sometimes we just want to look at an equation and determine its period. Again, you might like to stop the video and try that one for yourself before you reveal the answers. Okay, we identify in the first one here that the number in front of X is 6. So B is 6. The period is 2 pi divided by 6, which cancels to pi and 3. The period of this function is pi and 3. For this one, we identify that B is 0.5, the number in front of X. So the period is 2 pi divided by 0.5. 2 pi divided by 1/2 is 4 pi, is the answer. In our last example, sometimes we need to look at a graph or examine a graph, and by thinking about transformations, we can work out what the probable equation is. So we need to find the equation of this one. Well, we look at it and we see, again, maybe you want to stop the video and try it for yourself. But we look at the graph and we see the principal axis is y equals 1. This is the mean line, the line about which the point oscillates. So that immediately tells us, if we're writing it in the general form, that D equals 1. The number on the end is going to be +1. The amplitude, the distance, maximum distance from the mean position, is 1. So that tells us that A equals 1. There's no horizontal translation. So that means C equals 0. The period is pi. Okay, there's one complete cycle here. And another complete cycle here. So the period is pi. And that means, because pi is 2 pi over 2, it means that B equals 2. So we have identified A, B, C, and D in the general form. So A goes here, is 1. B goes here, is 2. C, well, that was brackets X takes 0, so it's just X, and on the end is plus D, so we'll identify the equation. Okay, I hope this video and the examples help you to do the exercises that are coming up. Just one last thing before we finish the video. Here's a little saying for you that's appropriate for this sort of work and maybe for this sort of time. It's a favorite saying that I've given to students a lot when the work has become challenging, or we're in challenging times. A smooth sea never made a skilled sailor. Think about that one and what it means.